For decades, humanity has looked up at the stars and wondered, could we actually capture that fire? Well, where we're diving into one of the most monumental quests in human history. We are literally trying to bottle the blazing power of a star right here on Earth. And you know what? This isn't science fiction anymore. It's an active, heavily funded pursuit that could fundamentally rewrite our future. I want you to imagine a world where we can tap into the exact same reaction that powers our sun. I mean, it's the ultimate fix, right? A way to generate limitless, clean electricity for all of humanity. Instead of relying on finite resources or burning fuels that just choke our atmosphere, we're essentially taking notes from the cosmos. We are trying to replicate the universe's ultimate energy engine.
All right, Section 1, a sun on Earth.
So the fundamental goal of fusion technology is to take that incredible, massive engine of our sun and shrink it down to a localized human scale. We're literally trying to build miniature stars inside laboratories and power plants. And mastering this? Well, it means completely satisfying our energy needs with the most fundamental power source in the universe. It's all about bridging that massive gap between the immense scale of the cosmos and the strict confines of our terrestrial power grid.
Moving on to Section 2, splitting versus combining atoms. Now, when people hear the word nuclear, they usually think of traditional nuclear fission. And fission works by taking heavy, unstable atoms and fracturing them to release energy. But tomorrow's fusion power, it does the exact opposite. Instead of splitting them apart, fusion violently forces tiny, lightweight hydrogen atoms together. And here's the crazy part. Because the resulting unified atom actually has slightly less mass than its original separate parts, that missing mass is converted entirely into energy. We're combining rather than dividing, and that subtle shift in atomic physics changes absolutely everything about how we produce energy.
Which brings us to Section 3, the ultimate energy promise.
The utopian promise that this atomic combination offers our future is just unmatched. First off, it promises staggering amounts of electricity with virtually zero carbon emissions. And unlike the legacy of traditional fission plants, fusion generates far, far less long-lived radioactive waste. Plus, the fuel itself is derived from hydrogen isotopes. These are incredibly abundant, like they can literally be extracted directly from seawater. It's safe, it's clean, and it's essentially endless. It is, for sure, the undisputed holy grail of electricity generation.
But it's not easy. Section 4. The 100 million degree challenge.
100 million degrees Celsius. Let's just put that into perspective for a second. That is significantly hotter than the core of the sun itself. Out in deep space, immense gravity crushes atoms together. But here on Earth, since we don't have that crushing gravity, scientists have to compensate with sheer brute force heat. We actually have to heat the field to over 100 million degrees just to force those tiny atoms to overcome their natural electrostatic repulsion and collide. Just think about the insane engineering required to build a machine capable of holding something that hot without instantly vaporizing. At that unimaginable heat, the fuel transforms into a super-hot plasma. It's this incredibly volatile, charged state of matter. So the magnificent challenge isn't just sparking this plasma, it's caging it. Scientists use massive magnetic fields inside these complex machines like tokamaks to hold this swirling mass of star stuff basically suspended in midair. And they have to keep it perfectly stable long enough for it to achieve ignition. That's the critical tipping point where our miniature star actually generates more energy than the system consumes to keep it running.
This leads us to Section 5, the commercial reality debate.
Look, we're no longer just sketching equations on chalkboards here. We are currently seeing billions of dollars in private and public investment pouring into this space, and driven by this massive influx of capital, along with some highly publicized milestones, like national laboratories finally achieving those brief historic moments of net energy gain. This technology is aggressively inching closer to the grid. The momentum is just palpable right now. We're closer to bottling a star today than humanity has ever been. Yet, despite all those billions invested and the brilliant minds hard at work, experts are fiercely debating the timeline, so we're left facing a pretty profound question. How quickly can this utopian energy source become an affordable, widespread reality? Are we talking a decade, or is it going to take half a century? The physics are proven. I mean, the stars do it every single day. But mastering it here on Earth remains the absolute ultimate test of human ingenuity. Just imagine what our world will look like the day we finally plug our cities into a star,